Welcome everyone. Kicking off with the first talk, and indeed going beyond tabular data. As AI engineers or machine learning experts, we all know how it is to work in these kind of data, where we have maybe free text or data sets with variables and targets. But there's also a different family of neural network architectures, and I really want to also give some inspiration there and see, okay, maybe you could use this in your day-to-day work. And I'm also quite curious, does anyone of you already use graph neural networks or anything in that sense in their day-to-day work? One hand. Two hands. Three, maybe, okay. So not a lot of people, so I think the perfect target audience for this talk, because we're going to do a quick dive into these networks and also, or this family of models, and also, okay, what's their intuition and how do they work and how do they learn this data, and what is exactly the difference between, the normal, CNNs or RNNs, transformer architectures that we are using compared to this graph neural networks, and maybe what are the correlations or similarities between them. So let's get started. So this is us. This is us programming our nice AI models, and we have our Ubuntu or Mac open, and we're training some models on, as I said, maybe normal data sets with some kind of features, maybe some time series analysis that you want to do with recurrent neural networks, maybe NLP, or nowadays, of course, large language models that are conquering that field. And maybe you're doing something in audio, so using some spectrograms to go from speech to text or the other way around. However, our world is not built on this data by itself. Our data or our world is shaped by the objects in it, in our world, and how they interact with each other. So certain objects have relations to other objects, and they also have valuable information in in that data. So what's that graph data in real life? Well, first of all, I think most of us would like fantasy. Sorry for the low-res picture, but this is the social network analysis graph of the Game of Thrones, or A Song of Ice and Fire, where we can see what kind of characters are, had contact with other characters and know each other and talked with each other. So definitely some features there. We have it in citation networks. Of course, a lot of research is linked back to each other, and we can do actually analysis on that. For example, are there some ego nodes? So, we probably all know Jan LeCun, for example, someone that brings a lot of interesting research and a lot of cited from there. So can we do some analysis from these kind of networks, so social network analysis? Well, of course, we know Netflix or any other social media that uses recommender systems. So actually using that or these systems to get some insights there and recommend you movies, reels, or any other data. And also bioinformatics. So especially these structures lend itself to graphs as well, where each node is a chemical or a molecule, I must say. I wasn't that good at chemics, but or biology. And of course, from this, especially looking back at Netflix, what I suffer from is this doom scrolling, where I get recommended all this content which really fits my profile. And they've TikTok or Facebook Meta has really gotten into me. So what I want to give to you in this presentation is that connectivity is key. So these connections between features that really give some insights in your data and also lets you do very powerful things with that data. Well, really short, who am I? What do you have here in front of you? I'm Chris van Riemsdijk. I'm an AI consultant at Data North. We do all kind of custom projects for clients, and next to that we do some workshops and webinars. I have a master's in computing science, where originally the track was called Data Science and Systems Complexity, but they renamed it now to AI Engineering. I think that's a way more suitable title to also what I've done. And I love to cycle and cook when I'm not behind my computer. And what's kind of the inspiration for this talk? Well, that's actually my master thesis, which was about water distribution networks. Here in the Netherlands, it's pretty good, our water distribution network, so how that is, and also the resilience to leaks, However, what we can see in third world countries or also Southern Europe is that there are actually a lot of problems with leakages in water networks. So think of sewers where, well, it takes a lot of expert knowledge to actually get or see in the data if there's a leak or not. So I've actually used these graph neural networks to train on networks and actually do some regression on node and edge level, and from there we can actually detect leakages with certain algorithms. That won't be the topic of today, but I kind of want to give you an understanding of the intuition of graph neural networks and how it works. And then I have this very scary next equation, but in essence, I kind of want you to get this mathematical equation, and I will definitely explain it furthermore and give some more insights that this is not some gibberish. So first of all, as only a few have worked with graphs, I don't know what the level is. Let me give like a quick overview of what are actually graphs and what makes them different from the normal data that we use. So a graph has certain attributes and is defined by the graph with its vertices, edges, and some global attributes. So a simple graph is defined on the left side, where the vertex or node can have attributes, so an identity or a number of neighbors, maybe the in degree or the out degree. So these are some kind of terms that are used in graph theory. Some edges that can also have some identity or weight. Maybe some certain weight has a way bigger weight than another weight. Think of bindings in this biology or biological structures, where we can have maybe 3 or 4 bindings even in these structures, and some global attributes. So what's the longest path, for example, in a network? Sorry, I went to, so indeed the nodes, the edge, and then the global or master node attributes. Next to that, we can have directed or undirected edges. So information flows through a network in particular systems. So think of the sighting network, where this could go from one researcher and someone else cites it. Or I think in water it's pretty clear as well. It flows to, for example, the houses, and it doesn't flow back ideally. Well, and how do we actually define these in mathematics? Well, we have our biology or molecular compound, and we have this adjacency matrix. In this sense, it's symmetrical, but in a social network setting, this doesn't need to be symmetrical, where we can have outgoing edges but not incoming edges in that sense. So it is not directed in that sense, and we can define that as a simple graph on the right. So, okay, we have this data where we have these vertices, we have these edges, we have these global attributes, but what can we actually do with this data? How can we do some certain tasks? Well, and there are some certain tasks that we have for graph neural networks, and those are graph level tasks. So again, to these biological compounds, we have input, we have some disjoint graphs, and we can do some classification on them, for example. So we can output a label for each graph. So does it contain 2 rings? Could be a hypothesis of this class. And how does this relate to standard or other toy data sets that we might know? Well, for example, the MNIST data set, where essentially we could also make an image, a graph, where each pixel is connected to its neighboring pixels and give some or weights to that. And then we classify at the end just which digit is it. Next to that, we have the node level, where we can actually detect on node per node basis. So an input is a graph of unlabeled nodes, and we can actually output a graph with node labels, and these can have certain features. So this can have just the embeddings itself from the nodes, but also maybe the in degree of a node, or the connectivity of its node, and maybe also its connectivity of its neighbors. Also a kind of spoiler already. And we can also relate this with image segmentation, for example. Oh, sorry. Yeah, then I'm slanted. Yeah. Yeah, okay. Yeah, I think this is better. So we can also relate this to image segmentation, where each pixel is defined by itself, just as in a node level. And next to that, we also have edge level predictions that we can do. So we can have a fully connected graph of unlabeled edges, and then actually classify the labels by itself. And this might be a, well, not so clear picture, but let's say these are persons in a 3D setting, and then we can actually define the persons as nodes, and what are actually the relations between them. So I think this is from a toy data set, which is the Karate Club data set from graph neural networks, where we can actually train a model to actually see, okay, what kind of person's watching, or are they fighting, so, and capture relations there. And also prune the edges that don't get any classifications, as they might not actually have any relationship with them. So you start with a fully connected graph, and you prune the ones that don't get a proper classification. So how do we present data to this graph neural network? We have, and how do we handle this? So let's look back at these, well, the citation network that I've shown before. Well, as said, we have nodes, we have edges, and we have global context. Well, maybe a sharp eye could have said, okay, let's put that in a tabular data, and each column is a node with its data over time, and then I'll train that. And yes, that's true. You could do that, and then probably you can already get some good results from that, depending on the task that you want to do. But the key, going back to it, is the connectivity. So how do we actually handle this connectivity that we have from these edges, from these nodes, that this internal data that we have, how do we actually map that? And that's not easily done in tabular data. And one example that I've already shown before is, or are adjacency matrices. These could be an option, a viable option, but there are quite some problems with that. They are not permutation invariant, as you can see, because this is the same graph, and these are all the adjacency matrices that you can make with it, and also different adjacency matrices mean the same thing. So actually, we have some overlap here in data. Luckily, we have a solution, of course, for this, which are adjacency lists. Well, just going back to this, this also produces really sparse matrices if you scale this up, of course, because especially in this data set, you could scale up to millions of nodes and edges, and then this will actually result in very sparse and memory inefficient data sets. So one of the solutions that is there is a adjacency list, where actually we go quite well. We decrease quite a bit from a quadratic amount of nodes that you have to just the amount of edges that you have. And this adjacency list, what you can see as the third time, where it's just a list of the connected nodes that are in your data set. So what is a graph neural network? It was quite a long sentence, but I try to put it in there. GNN is a optimizable transformation on all attributes of the graph that preserves graph symmetry. So this permutation invariances, and that means that we go by a principle of graph in is graph out. So we're actually using, well, we're training embeddings, and at the end we can maybe use another function, which could be, if we can make a derivative out of it, then we of course can use an MLP or another neural net there. And that is, for example, in the case of the biological structure, we can actually write this molecule in a lot of ways, and we kind of want that to be invariant of it, that it doesn't matter how we actually put these edges and nodes in each other, the relationship itself should remain the same and have not any influence on your output of the model. So how are we actually going to build this building block? Well, I said we're going to adhere to this graph in, graph out structure, where we have the global components, we have the nodes, so the vertices and the edges. And this graph layer that we can have can just be a update function in there. So we are actually updating the nodes attributes from layer n to layer n plus 1. And this can be just, as said, like an update function, which can just be a multi-layer perceptron, for example, if it's just if you can derive from it. So, of course, now we can create one simple layer with a graph neural network. How can we actually solve a task? Well, for example, if we want to do node level classification, we can take the feature embeddings that we get from this graph, throw it in another classifier, and then we can get node predictions from it. So in this example, toy example, it's binary classification. So from these node embeddings, we can actually say yes or no. And in the sense of the toy data set of the citing articles, you could say if they are related to each other or not, for example, some kind of offers. However, we don't always have information on our nodes or on our edges, and we kind of want to switch between those. So what we do is pooling, and pooling is a way of going around things to actually pull all the attributes from your edges, for example, on a node. So as you can see in the example here, if we look at the node with the black outline, it has 4 outgoing edges, or incoming, how you can, it's undirected, so it doesn't really matter. And you can actually take the embeddings from those and then aggregate them at the end. So you take a max, a min, a mean, doesn't really matter from this. And what does this mean? That you can also go from, if you have only edge data, that you can also go to node predictions and the other way around. And there's actually pretty active research on how you can actually, if you can do node and edge prediction on the same time, and how can you actually, should you do the pooling first to the node layer or the embedding layer or to the edge layer? Because you also have like a neural network in there, so it depends on when you actually do your update step, which is still very active research. But here, for example, from edge embeddings, you can do node predictions as well. So this pooling function just goes from edge to node to edge, goes the same ways. So we have this end-to-end GNN pipeline, which is still very, very simple, where we have this input graph. We have multiple GNN blocks, which are just stacked multi-layer perceptrons, for example, which gives our transformed graph with different feature embeddings for nodes, vertices, and the global features. Then we can, for example, put a classification layer there, and then we get a prediction. So node, edge, or global predictions. And these are very easily scalable to regression tasks or other similar tasks that you want to do. However, now we are still very, very local, and we don't really get the benefits that we have from graph neural networks. And this benefit is message passing. And if you know your CNNs, your convolutional neural networks, this might sound similar, because that's kind of the idea that you have with CNNs as well. So what we want to do is make networks topologically aware. So instead of, so also get data from the neighbors and also aggregate them in your feature embeddings. So in layer N, we might do your 1 degree or your 1 hop neighbors, but you also might want your information, or these get updated from the neighbor also gets updated, so you get this message passing system through the whole network. So in a really small network, you could be done in 4 or 5 layers where you get all the data. So in the end, we have this message passing where we also use a transform information, which is, again, for example, MLP could be any differentiable equation, just so you can do some backpropagation to learn the system and update your parameters. And then we can update our new graph. Well, how does that look like? Like this. So at the end, we do some pooling already and do some function embeddings before we do the update step. And this creates a graph convolutional layer. So like the basics of a GNN. So what we do is, for each node in the graph, we gather all the neighboring node embeddings. We aggregate those, so by a sum, max, or mean, just that you get back to your proper dimensions. And then they are passed through an update function. Well, and that kind of brings us to the mathematical equation that we had here, where we get all the node embeddings from our... Okay, let's start at the left. Those are, for example, our new node embeddings. Then we have our gamma k, which is an update function, which takes as parameters the current node embeddings from the previous layer, but that's kind of the current, and the k is the new one. And where we loop over all the neighbors, and the big cross is just the aggregation symbol, so that's a sum, max, or a mean operation, for example. And then a new multi-layer perceptron or another neural net that takes in the node embeddings from itself, the neighbor, and, if applicable, the edge that is between those. So in essence, not that hard. And how does that look visually? Well, for example, if you look at the lower left node, those will actually talk with its neighbors will talk to its neighbors, and then how bigger or how deeper we make this network, how more message passing we get. So all nice and all, but how do we start? Maybe this could be a very hard thing. Well, actually, we have PyTorch Geometric, which is perfect because it's a library built on PyTorch. You can easily write and train GNNs on that. You can have toy data sets, just like the MNIST data set that we have in Torch, but also a lot of other things. And especially what is very nice, it's built on it, but it's also exactly the same API. So we exactly use the same functions, methods, etc. It's all the same. It supports mini-batching already, so also nice for your regularization. So an example of PyTorch Geometric is this, where we create our edge indices. So these are these adjacency lists. We create a torch tensor, so it's all based on torch. And then the only thing is different is that we have some data object that is encapsulating everything, where we can also give this connectivity. And that is just seen as this, for example. Well, model definition, not a problem, I would say. Just a torch NN module again, exactly like an init, where you create all your layers, and then you forward through your network. So the GCN conf that we are seeing here is actually the layer that I've showed you before. Training loop, also not a problem at all. We just create a device, a model, we set everything to the device, and we do our standard training loop of zeroing our gradients, doing the forward pass, doing a backward pass, and optimizing. So I wanted to do a quick demo, always scary, but made it very foolproof, I would say, for myself, where we train a little network. Let's see if I can. Boom, perfect. That's very readable, I think. So I don't really see my screen, so I'll go down. So these are kind of the code snippets that we have seen. With a GCN, we do some data sets. We implement that. So this is the built-in one that just pulls it from their hub. We create our model definition with 2 layers, and we do node classification here. So this is the data set of the citations data set. So at the end, we want to do some training, some validation loss that we want to do. And what I really, really like about PyTorch, it's very experimental still, but we have this explainer class where we actually can also explain some certain things that we get from our output, so we can actually see per node. And this is really important in social network analysis, for example, that there are, most of the times in these networks, there are some ego nodes. So there are some nodes that are really congested, and we actually want to do some research on that. And then from this, we can actually do some extra analysis that is built in PyTorch. Now, I want to run it. Now you need to trust me, of course, but then is it running for you? Of course, I don't have a. See, that's always scary. But I have some graphs. Oh, it is actually running. Great. Hooray. I think it's fixed now, so yeah. Thank you. Oh, yeah. It's a bit annoying with the 2 screens. Where's my cursor? At the top? Ah, perfect. Thank you very much. So from this, we actually get our feature importances per node, or this is for node 10 in this data set. And what we can also get is the subgraph, and we can actually see like how the opacity actually shows how important a particular node is in some n-hop distance to the and it's node 10 now, so we can see that 2, 5, 4, 5, and they don't say a lot now, but I think it's good to show what you can actually do with this data. So play will it work? Perfect. So what we didn't cover yet, there's so much more to this than only this talk that I can do for 30 minutes, is graph attention, networks, of course, now everyone should be excited now with the current transformer hype. What we normally do is weight these node or feature embeddings or edge embeddings that you give to the model. But you can also do this with attention. So here we can actually see that these weights are, we see this famous softback function again at the left, where we can actually see some weights. And this is, I think, a free head attention network that you can actually do to concat or average your feature embeddings. And next to that, you don't have only homogeneous graphs, but you also have heterogeneous graphs, where there are more disjoint graphs that actually also have these connections with each other. And you can also do some analysis on that, where you essentially have some parallel networks that are with the forward pass, and there you can do some analysis on that. So I hope this goal that I had of giving you some understanding of the intuition of graph neural networks helped. And the takeaway message, of course, is connectivity is key. I think we have 5 minutes left for questions, so thank you very much.